Wonderful. And whenever you are ready, let's go ahead and thank, well, I guess thank, yes, Dr. Catherine Greenhill for speaking today. And I'm really looking forward to hearing this talk on Markov chains and stable degree sequences. So whenever you're ready, Catherine.
Okay, thanks, Erin. Sorry for the time difference mix-up. I think I should have double-checked that as well, but I'm very pleased to be here talking to you. There's always been a lot of women in combinatorics in Australia, and I think that's in a large part due to the women who were lecturers and professors when I was coming through at the University of Queensland, Anne Street, Liz Billington, and Sheila Williams and others. So I'm very grateful to the role models that they provided for me. I'm going to tell you a bit about some work on the mixing time of a particular Markov chain for sampling graphs with given degree sequences and connections that have come up with the notion of stability for degree sequences. And some of this is joint work with Jane Gow, another woman in combinatorics from Waterloo who apparently was here earlier, might not be here now. So graphs, my graphs are finite, labelled by the vertex labels are 1 up to n, and we're interested in graphs with a given degree sequence. So this is a sequence of usually positive integers, could be non-negative integers, and we don't assume that the degrees have been sorted into non-increasing order. We just say that dj is the degree of vertex j. And then a sequence is graphical if there is a graph with that degree sequence, and we basically just consider graphical sequences. So anytime you draw a graph, the corresponding degree sequence is graphical, and this is just showing that the degrees are not sorted in any way here. Okay, but we want to do asymptotics. So we don't just have one degree sequence, we actually have a sequence of degree sequences indexed by the number of vertices n. So not only does the length of the sequence depend on n, but also the functions in the entries might depend on n. So, you know, vertex 2 might have degree square root n, for example, or the ceiling of that. So the degrees themselves can be functions of n. But we usually suppress this extra of n on the degree entries because it just gets a bit unwieldy. We want to turn n to infinity. Sometimes that has to be along a subsequence like the even integers for divisibility reasons. And then we can do asymptotics. So I said that already. We just write D and we don't always remind ourselves with the notation that we do have infinitely many of these, but we always do. Okay. So now I'll just let G of D be the set of graphs on the vertex set 1 up to n, which have the given degree sequence D. And if the sequence is regular, D regular, then we'll just write GND instead. And what we want to do is to have some algorithm or process to actually produce a random element from this set. And we want to do that efficiently because we might have to do it many times. So in this forum, hopefully I don't have to persuade you that this is something that people are interested in, or actually we might just say we want to do this because it's fun and interesting and we like to think about these problems. But actually there are people out there who really do use graphs to model the systems that they're interested in, and they are genuinely interested in efficient algorithms for this problem. So yeah, that's what we're going to do. And again, we don't just have one set of graphs with a given degree sequence, we really have a sequence of these sets of graphs, and we're interested in asymptotics. And there has been a lot of work on this problem, and I won't be surveying all the different types of algorithms today. I'm actually, last year I wrote a survey paper, and in July I'm going to be an invited speaker at BCC. So there'll be much more details. I'm sort of deferring a lot of that to that survey or that talk. Eek! Invited speaker, yikes. So that's exciting. And today we're going to talk about the Markov chain approach to this problem and just focus on that aspect. Okay. The rough plan for the talk, I'll just have a sip of water, is as follows. I want to remind you of all the background. I'm not going to assume you know about this stuff, so I'll give you the background definitions on the Markov chain, stuff that you need to know, and the canonical path technique, which is often used in this area. Then we'll talk about Markov chains for sampling from graphs with a given degree sequence, and bring out the connections with the stability of degree sequences and some of the recent work. I'll be hiding quite a bit of the technical details, but I'm hoping that you'll get a flavour for the arguments and understand why the connections come up. All right, so here's your Markov chain basics. We have a state space or set omega, which is finite but very large, and a Markov, that for me. And so a Markov chain is a stochastic process which starts at some state x naught, which could be fixed or it might be random. And then at the state at time t, which is xt, it decides what to do next randomly, but just based on where it is at time t and not how it got there. So the probability that it moves to a particular state in the next step only depends on where you are right now and nothing that happened in the past. So this is called memorylessness. And as I said, xt really depends on n. It's a random element of the state space omega, which also depends on n. It's usually finite but exponentially large. And you can think of it as walking around on some underlying graph of the state space. You're making a random choice of where to go next and moving along an edge. Often for me, what you do at time t is independent of the time. It's just based on where you are right now, and then you make a decision. And that's called time homogeneous. So if your Markov chain doesn't look at its watch when it decides what to do next, then you can put all the information about the decisions of the chain into something called the transition matrix, which just stores the probability that in one step you move from x to y. So it's the probability that the next state is y conditioned on the current state being x, and this is independent of t. And then the transition matrix really controls everything about the chain. Okay. So I tend to work with Markov chains that are essentially as nice as they can possibly be. So that means they're ergodic, which is irreducible and aperiodic. And irreducible means that you can get from any state to any other state using a sequence of transitions of the Markov chain. Aperiodic takes a little bit more to write down, but you think about any state and any way that you can get from that state x back to itself using a sequence of transitions of the chain, that gives you the sort of length of a closed walk in the underlying graph. And you need the greatest common divisor of all those possible lengths to be 1. So that you want to avoid bouncing from one side of a bipartition to the other. And if that greatest common divisor is always 1, then the chain is aperiodic. And if your state space is connected, it's enough to just put one little self loop, one positive probability of staying put somewhere. And often we just make sure there's always a positive probability of staying where you are at every state. And then that certainly guarantees aperiodicity. Okay. So why do we like ergodic Markov chains? Ergodic Markov chains are irreducible and aperiodic. And it means that there's a unique stationary distribution pi, which is a limiting distribution. So if you run the chain for many, many steps, the probability that at time t you're at the state y tends to the stationary probability of y, and it's independent of the starting state. Okay. So you might say, well, how do I find the stationary distribution of a Markov chain? But actually, in my work, we usually do it the other way around. We start with the desired stationary distribution and we design the Markov chain to make sure it has that distribution as its stationary distribution. And there's a nice trick that makes this quite easy, which is detailed balance. So if the Markov chain is ergodic and it satisfies these equations with respect to some probability distribution psi, then psi is the stationary distribution. And what these equations say is the probability that I'm at x under psi at state x and that I take one step in the Markov chain and end up at y is exactly the same as the probability that I'm at y under the distribution psi and I take one step and I end up back at x. Okay, those two things are equal. This is also called time reversible because it means if you observe the chain and you watch what's happening with the chain, you can't tell whether the chain is running forwards or backwards in time. So these are really nice equations. If psi was the uniform distribution, right, then you can cancel here and it just says the transition matrix is symmetric. So if you have a symmetric transition matrix and an ergodic chain, then you know you have the uniform stationary distribution. Okay. So how quickly does a ergodic Markov chain converge to its stationary distribution? We know the stationary distribution is the limiting distribution, but in a practical sense, it's not great to tell someone to wait infinitely many steps and then they'll be sampling exactly from stationary. They want to wait some specified number of steps and know that they're sampling from a distribution that is sufficiently close to uniform. Okay, so in order to answer this question, we need an idea of how far two distributions are away from each other. So we need a metric on probability distributions on omega. And we tend to use the total variation distance, which is half the one norm between the two, if you think of them as sort of vectors. So it's just defined like this. And the half is convenient because it means the total variation distance is also the maximum difference in probabilities of any event. Take the maximum over all possible events. And now that we have the total variation distance, we can define the mixing time of the Markov chain, which takes an input, which is epsilon, which is how close to stationary you'd like to get. And then the mixing time is the worst case overall starting states of the number of steps required before the total variation distance from stationary of the distribution of the state at time t starting from x. So I haven't really defined this on the screen, but PTX is the probability that if I start at state x, which is a fixed state, and I take t steps, what's the distribution I end up with after those t steps? And that's this. So we'd like that to be close to pi. And because of the way Markov chain works, once that distance is less than epsilon, it's going to stay less than epsilon forever. And so this is a good definition for mixing time. And it just guarantees that after this many steps, you're always within epsilon of uniform or of your stationary distribution. Okay. So the aim then, if you want to use a Markov chain to do almost uniform sampling from a set, is you want to show that your Markov chain is rapidly mixing, because that says that tau of epsilon is bounded above by some polynomial in the logarithm of the size of the state space and the logarithm of the inverse of the tolerance. And because the state space is exponentially large, this ends up being something that's polynomial. And it also kind of tells you that the tolerance can also be exponentially small because we only end up with the logarithmic factor of the inverse of the tolerance here. Okay, so it is a strong condition because you want to get exponentially close to stationary over an exponentially large state space in polynomial time. Okay. Now, we also know from linear algebra, what we're doing here is just taking powers of the transition matrix. So really, the eigenvalues of the transition matrix control everything. They control convergence rate of the Markov chain. So you might just think, why can't we just calculate the eigenvalues and figure this out kind of precisely? But the point is that the state space is too big and the transition matrix has the same size as the state space. So it's not feasible in polynomial time to calculate these eigenvalues. So instead, some methods like coupling just sort of directly try and get a handle on the mixing time, but a lot of the other methods go through the eigenvalues. So they kind of sneak up on the eigenvalues and bound things like the spectral gap. That's what we're going to do using geometric arguments. So here is a picture, very simple pictures, but you're meant to picture something bouncing around inside both of these states, some sort of Brownian motion or something, and you ask yourself, which picture do you think would encourage rapid mixing for a uniform distribution where I want to spread out over the entire state space relatively evenly, okay? And if I asked you to vote, I think probably a lot of you would say, well, the one on the left looks like you can more freely walk around, right? The one on the right has this really narrow sort of bottleneck where it's difficult to get from one side to the other. And that's a fact, that if there is some constriction in the state space that makes it difficult to escape from some area, then it makes it very difficult for the chain to spread out evenly over the state space, and you end up with an exponential mixing time. And conversely, if you don't have any of these bottlenecks, then the chain can walk around very smoothly and hopefully spread out over the entire space sort of quickly, and you get rapid mixing. And Jerram and Sinclair introduced this idea of conductance to make this precise, and it gives you bounds on the mixing time, both from above and below. So a lot of arguments go through conductance, but then you can ask, well, how do I get a handle on whether or not I have these constrictions? Okay. And one way to do that is to use canonical paths. So we are going to just look at all possible pairs in the state space. So take a pair of states, and we're going to define, for the moment, one path from X to Y, a canonical path, where every step in the path is a transition that the Markov chain might take, okay? Then we do this for all pairs of states, and so now we have a big set of these paths. And then we ask ourselves, we look at each transition, say the transition from Z to W, and we look at, it's kind of like the number of paths that are using this transition. It's actually weighted by things like the probability of Z and the probability of W in the stationary distribution, but in the uniform distribution, it's essentially counting. So you want to know how many paths are going across this particular transition, and you define something called the congestion that I'm not going to define formally. But the idea is, if no particular transition has a very high congestion, then there can't be any small bottleneck, because anytime you have a bottleneck, the transitions that go from one side to the other will be heavily loaded because they'll be carrying a lot of paths, okay? So you calculate a bound on the congestion and you apply a result from a paper by Alistair Sinclair usually. So that's the canonical path method. And what we've really been using to analyze the mixing time for these chains sampling graphs with given degrees is a generalization of that called multi-commodity flow. And what that means is to try and spread the load out even more smoothly, rather than use one path between X and Y, we're going to define a set of paths between every pair X and Y, and we sort of average the flow from X to Y. Instead of going along one path, we send it along a bunch of paths. And that just helps to smooth things out even more. Same paper gives you bounds to ways to bound the mixing time if you've got the congestion under a multi-commodity flow. But in this talk, I'm going to sort of blur the boundaries and really just, we can think about a canonical path. Okay, so as Erin said, let me know if there's any questions at any point. All right, so those were the basic definitions about the Markov chains. And now we can start talking about sampling graphs with given degrees using Markov chains. So what we want now is a rapidly mixing ergodic Markov chain with a uniform stationary distribution on our set. Or, just to throw one additional idea in, if the state we want to sample from is this blue set here, it's also possible to expand the state space a little bit, or even a polynomial amount, and get some bigger state space. Maybe it's easier to sample from within the bigger state space. So you do some walk in this larger state space, and when the mixing time is up or your bound on the mixing time is reached, you stop, you have a look at the state that you're at, and you ask yourself, is this state in my desired set, the blue thing? And if it isn't, then you just throw that out and start again, and you start walking around, and every so often you'll end up in the blue set, and that's when you give output. That's called rejection sampling. And so the running time, the expected running time of an algorithm like that depends on how small a proportion the blue set is among the larger state space. Okay, so using this idea, Jerram and Sinclair were the first ones to describe a Markov chain for sampling graphs with given degrees, because they had a Markov chain for sampling perfect and near perfect matchings of a graph, and they could transform the degree problem into this problem using a construction of tuts. But in terms of what's happening on the graph, I can tell you what the chain does using this example. So here's a labeled graph. The chain randomly chooses a set of two distinct vertices. And in this case, it's chosen 2, 5, and we see that's an edge. So we're going to remove that edge. And now we have two vertices that don't have the desired degree. They actually have a degree that's 1 less. This vertex is supposed to have degree 4, but it only has degree 3. And, you know, this one's also missing something. So those are sort of deficient. And then you choose 2 more vertices, 2 more vertices. Maybe the next choice is 2, 6, let's say. And we want to insert the edge 2, 6, but the name of this game is we can't make any degree higher than what it should be. So it's okay to insert at vertex 2, but it's not okay to insert an edge at vertex 6, because 6 already has the correct degree. So what we do instead is we choose an edge incident to vertex 6, remove it, and then we can add the edge 2, 6. So we choose one of these 3 edges uniformly, and maybe we choose to remove the edge 4, 6 at this step. Okay, so that's one step where you remove one edge so that you can insert the chosen pair as an edge. And notice that that's moved the vertex with the degree deficiency used to be at 2 and now it's at 4. And then you keep choosing pairs, and every so often you're going to choose exactly the 2 vertices with the degree deficiency. And in that case, you can insert the edge and you've gone back up to the desired set where all the degrees are perfect, right? If I chose 4, 5 at the next step, I would just insert that edge and I would be back in the proper set that I want to sample from. So you can see that this is walking on a bigger state space. And we can define the state space here. So we're just going to write the 1 norm notation for the 1 norm. And so the state space of the Jerram-Sinclair chain, it's walking over the union of graphs G of D prime, where D prime is close to D. Every element of D prime is less than or equal to the corresponding element of D. And overall, the 1 norm, the sort of Manhattan norm, is at most 2. This means either you've got 2 vertices which have a degree deficiency of 1, as in these 2 pictures, or you might have 1 vertex with a degree deficiency of 2. Okay, so we've got this bigger state space. And and then we use this rejection sampling idea, and so the expected number of trials until we win is the inverse of the probability under the uniform distribution that you hit the desired set. So it's the size of the bigger set divided by the size of the original set of graphs, okay? And because we want a polynomial mixing time or a polynomial running time overall, we're going to need this number to be polynomial. And this is why we get now the link to a notion of stability for degree sequences. This was the first one. Jerram and Sinclair said that a family of degree sequences, graphical sequences, is p-stable, p for polynomial, if there's some polynomial p of n such that for any degree sequence in the family, if it has length n, then the size of the bigger set, G primed of D, is at most p of n times the original size, okay? So the expansion in this set is governed by some polynomial factor. And this, it doesn't make sense to talk about for 1 degree, you have to talk about a family of degree sequences up here. So what Jerram and Sinclair ended up with is showing that their chain is rapidly mixing anytime the degree sequence is p-stable. And the definition of p-stable just naturally arises from the probability involved in the rejection sampling. You don't want to be looking for an exponentially small needle in this larger haystack, okay? And yeah, so the notion of p-stability arose naturally And intuitively, what it means is that if you just change the degree sequence a little bit, you're not going to massively blow up the number of realizations that you get. Okay, small perturbations just make relatively small change in the number of graphs. Okay, so that's the Jerram-Sinclair chain. And together with Brendan McKay, Jerram and Sinclair looked at p-stability in more detail. They gave a couple of sufficient conditions, which I haven't written down in full, but in particular, they also looked at they gave some examples of p-stable families. And some of them are sparse. So capital delta is the maximum degree. If the maximum degree is at most 2 times the square root n minus 2, then that family of degree sequences is p-stable. Some examples are dense. For example, if the minimum degree is at least n on 4 and the maximum degree is strictly less than 3n on 4, that family of degree sequences is also p-stable. But it can't cope with everything. So the sufficient condition that Jerram, Sinclair and McKay proved does not cover heavy-tailed distributions such as power law distributions, except in a very trivial case. So usually in a heavy-tailed distribution, a lot of the vertices have very low degree, but there do exist this small number of vertices with really high degree, and they don't fall into any of these sort of families. This is a really kind of silly cartoon that's just meant to indicate a heavy-tailed degree distribution, because there's quite a lot of vertices of low degree, but there's a couple of hubs, these vertices here, of relatively high degree. Of course, in a real-world network, they are massive networks, and they look much more impressive than this cartoon. And a lot of real-world networks do seem to have heavy-tailed degree distributions. Okay, so that's the Jerram-Sinclair chain. And now I'm going to tell you about another Markov chain called the switch chain for sampling graphs. So this is the most natural Markov chain if you just want to walk within the set G of D and not expand the state space at all. So no rejection sampling is going to be required. You just choose a pair of non-incident edges randomly and replace them in one of the 3 possible ways chosen randomly. So you could put them back in, or you could rewire them like this, or you could rewire them like this, but you want to make sure that all the degrees stay the same. And if you perform this operation many times, you will randomize the graph. So you can think of it as a Markov chain for sampling graphs, but it's also been used in, let's say, a communication network, like a peer-to-peer network, to sort of re-randomize and heal local portions of a large decentralized network. Okay, now the switch chain, it's ergodic, the transitions are symmetric, so you get a uniform stationary distribution. And I'm going to introduce capital M is the sum of the degrees, which is twice the number of edges. Okay, here's some history. There's a lot more history, so I don't really want to say too much about all of this stuff. See my survey paper upcoming for further details. But we do know some degree sequences for which the switch chain is rapidly mixing. The switch chain has also been studied for bipartite graphs and for directed graphs. There was earlier work by Cannon, Tetterley and Vempala on bipartite graphs that I haven't put here. Unfortunately, there was a bug in their proof, but they did investigate the switch chain for bipartite graphs. Then Colin Cooper, Martin Dyer and myself, we were able to prove the switch chain is regular for is rapidly mixing for d-regular sequences of any degree. And I'll say a little bit about the method used. Then I looked at regular directed sequences. Peter Erdős, Miklos and Sukop looked at half regular bipartite graphs and used slightly different, a different canonical path argument. So the degrees are regular on one side, but don't have to be regular on the other. Then I managed to figure out how to handle irregular degree sequences, and we extended it to directed irregular degree sequences, as long as the maximum degree wasn't too high, essentially. And there's been a bunch of other related work. There's more things I could put here. So we knew, bits and pieces about where the switch chain was rapidly mixing. And the proofs are kind of long and technical, but they follow the same sort of skeleton, the same sort of steps. One thing that I found quite good was when I was trying to extend the original argument, the 2007 paper, from the regular to the irregular case. Even though there's lots of steps in this argument, there's really just one lemma where we were actually using regularity to get the lemma to work. So everything else just carried over. And then there was this one lemma that we call the critical lemma, where we had to think of something else. And I'm going to tell you a bit more about that later, because it's also where the connection with stability of degree sequences comes back in. Okay. Unfortunately, when you use the multi-commodity flow method, the upper bounds on the mixing time that you end up with, they're polynomial, but they're very high degree polynomial. They're sort of embarrassing to talk about. And so we don't believe they're anywhere near tight. And some people have done simulations that show that they don't seem to be tight. But on a theoretical level, we're happy because they're polynomial. And until very recently, that's all we had, these very loose bounds on the mixing time. But last year, Tikhomarov and Youssef put a paper up on the archive which proves essentially d squared n squared with some log for the upper bound for the mixing time of the switch chain for d-regular bipartite graphs. Okay, well, this is an amazing improvement. Here, d has to be at most n to some small constant. So this paper uses very, very analytical methods. It's sort of directly bounding the eigenvalues rather than sneaking up on the eigenvalues. It involves a Poincare inequality and a log Sobolev inequality. And I haven't worked through all the details, but the paper is being refereed at the moment. And I think we're all watching carefully to see if it's correct, because it looks amazing. So this was a very exciting result. Okay. What I want to do now, though, is give you a flavour of how you actually define a canonical path between two states in the state space, because we're going to need some of these ideas soon. So we want to get ourselves from x to y. Here's x, which I'm going to have in blue, and y, another state with the same degree sequence, which I'm going to show down here in the symmetric difference. Blue means x and red means y. We want to work our way using steps of the switch chain from x to y. And we're always going to be guided by the symmetric difference. So you have to look at the symmetric difference and sort of pull it apart into cycles that you're going to work on in what order. And that's a lot of detail that I'm not going to share with you. But let's say this is our symmetric difference. So first, you're going to hone in on one part of the symmetric difference where you want to make a switch. And maybe I'm going to choose these three edges and also the fourth edge that makes a 4 cycle here. Okay, this will take away 2 edges of x, introduce 1 edge of y, so we're getting closer to y, but it will also introduce an edge here that's not in x or y. And that's like a defect. So we've temporarily messed things up and introduced something that shouldn't be there, but we're going to fix that straight away. Now, sometimes the defect is we remove an edge that should be in both x and y, but we temporarily remove it and then we put it straight back. So this, we've just performed one switch to get ourselves from this state to this state. Okay, and that's one step in our canonical path. What's happened to the symmetric difference? It's become smaller, all right? Instead of however many, I guess 8 edges over here, we've got 6 edges now. So we're making progress. And now we choose another part of the symmetric difference that we're going to work on, maybe these 3 edges. And we, question?
Yes, this is the symmetric difference of what?
Oh, this second one, yes, good question. It's the symmetric difference of this state that is our sort of frontier of the path compared to y. So these two, I always compare to y, okay? So I'm going to just assume that that's okay and keep going. All right, I'm pretty sure these figures are correct. We're going to take these 2 blue edges and take them out. Notice that one of the blue edges we're going to remove is this edge that shouldn't be there anymore. So in this case, I guess blue doesn't mean x anymore. It actually means this current state. Yeah, mostly it's x. So we're going to get rid of this interloper and get rid of one edge of X here, insert an edge from Y, and again, we're going to be inserting an edge that completes the for cycle that in a way shouldn't be there. It's not in X or Y. So this edge here is another kind of a defect, but we're getting a lot closer to Y. In fact, when you look at the remaining symmetric difference between these two states, it's just a for cycle, which means that in one more switch, we can fix it up and we get all the way to Y. So this is the sort of thing that you do to get from X to Y. In this case, we've taken 3 steps. And we could call this a canonical path. What you actually have to do in the paper is explain precisely how to choose which part of the symmetric difference to work on so that a person can come and carry out that procedure without making any choices or guesses. So that's what we do. And now we have a set of canonical paths, or really we have a multi-commodity flow, and we have to analyze the paths. So we ask ourselves, earlier I said we ask ourselves how many paths go through a particular transition from Z to W. But actually, for an upper bound, we just look at the number of canonical paths that can pass through a given state Z. And to answer this question, we introduce something called encodings. So we identify X, Y, Z with their adjacency matrices, and we define an encoding by adding up X and Y and taking away Z. We'll see an example in a second. So these are almost graphs with the given degrees. It's a symmetric matrix with 0 diagonal. All the entries are either 0, 1, or sometimes you get a -1, or sometimes you get a 2. And the -1 or the 2 entries are called defects, and they correspond to defect edges. So for example, if an edge is absent in X and Y, but it's present in Z, then we're going to get -1 over here. And that is the defect edge of -1. That's what we saw in the previous example. And it's also a fact you can check that because X, Y, and Z all have the same degree sequence, when you add up the labels around a particular vertex, you'll just get the degree of that vertex. So here's the encodings for the 2 intermediate states that we saw before. And the red edges now indicate a defect edge with a label of -1. And you can see, for example, this vertex here has got degree 2. And down here in the encoding, I've got a 1 plus a 1 plus a 1 plus a -1. So the labels do add up to 2. So that's the idea of an encoding. Why are we looking at encodings? It turns out that if you have the current state and you have the encoding for that state, then you can recover the end vertices X and Y uniquely in the 2007 argument. And that's because of our very careful choice of canonical paths and all the details that I haven't told you. We also know a lot about the possible defect edges that you can get. We know there's at most 4 of them, and they form a subgraph of something that looks like this. So there's up to 3 edges that share a vertex here, and 2 of them could be -1 and 1 of them could be a 2. And then there's a kind of floating edge, which could be a 2 or a -1, and it may be attached to 1 or 2 of these leaves, but it can't be attached to the central vertex. So when you think about the options, it gives you 5 possible sort of shapes that you could get, and you might have a subgraph of those. Okay, so we know a lot about these encodings. And as I said before, almost everything works from the regular when you try to generalize to irregular. And here is the lemma that didn't just carry over. This is the one we call the critical lemma. So it turns out that in the proof, we want to show the number of encodings that are consistent with a state Z, I'll tell you what that means in a second, is at most polynomially larger than the state space. And the only thing you have to worry about is if you have a -1 defect, it has to correspond to an edge of Z, so that when you add them back up, you get a 0. When you add L and Z together, you need to get zeros, 1s, or 2s. So that's the only thing going on there. And whatever polynomial that you get here, it's a factor in the final bound on the mixing time. So you see, it's important that it really is a polynomial. Okay, so this might remind you of, well, it was very important before that we had a polynomial ratio between the size of the bigger state space in the Jerome-Sinclair chain and the original state space. And sure enough, this is how graphs with a slightly perturbed degree sequence come into it in the analysis of the switch chain. And actually, it took me a lot longer than it should have to make this connection. So an encoding is essentially a graph with a perturbed degree sequence, because what you do is you just remove the defect edges, and that affects the degree sequence. For example, with the degrees in circles for each vertex here in brackets, if I take away this defect of -1, then this vertex here, which is meant to have degree 2, will actually have degree 3, but it's now a proper graph with no defects. Okay, so if you have -1 defect edge, then you've got 2 vertices with a degree that's 1 higher than it should be. That's very similar to p-stable, except we're going up instead of going down. And so now we have a new idea of stability of degree sequences that's again come in fairly naturally. So there's a bunch of unifying results where people tried to combine some of the big list of results that we had before. Amanatidis and Clear gave a new notion of stability for degree sequences, which was to do with, in the larger state for the Jerome-Sinclair chain, how many steps you need to get into G of D itself. And if it was at most some constant k, then you get a polynomial n to the k coming in the mixing time bound. If you're strongly stable, then you're p-stable. And they proved the switch chain is rapidly mixing for all strongly stable degree sequences. And they showed an analogous result for bipartite graphs. And that, at the time, covered all that we knew about the switch chain on graphs and bipartite graphs. And then more recently, together with Peter Erdish and his team, we were able to give slightly different canonical paths and prove that the switch chain is rapidly mixing whenever the degree sequence is p-stable in the setting of graphs, bipartite graphs, and directed graphs. And again, we used a different analysis to the original one, but we ended up with graphs that had at most -1 defect. And as we saw before, that is practically the same as p-stable, except you're going up in degrees by 1 rather than going down. So that was a nice result. Okay, but now I want to tell you a bit about what I did with Jane. We introduced a new definition of stability because the world just needed some more. We say that a degree sequence is k alpha stable if for any graphical degree sequence d primed, which is within L1 norm of k from the given degree sequence d, the size of that state space, the number of graphs with degree sequence d prime, is at most m to the alpha times the original, where m is the sum of the degrees, so twice the number of edges. And then you can form the set of all degree sequences that are k alpha stable. And here's the real definition. We say a family of degree sequences is k stable if there exists some alpha such that every degree sequence in that family is k alpha stable. And we prove that 2 stability is equivalent to p stability. So we capture p stability in this definition. And here's a couple of things we were able to prove. If D is 8 alpha stable for some alpha, then the switch chain is rapidly mixing and we get an explicit mixing time bound, which is proportional to m to the alpha. I feel like I'm running out of time, but I'm just going to give you a little idea of the proof here. You think of all the graphs that can arise from taking an encoding and removing the defect edges, okay, like we did before in that example. So those degree sequences will be different from D, but we show that the degree sequence of H is within at most 8 in L1 norm from D. So we can take K equals 8. And then because we know this, and we know that it's 8 alpha stable, we know that there's at most m to the alpha times the size of G of D choices for H. And then we just have to put the defect edges back in. And if you trust me, there's a polynomial number of ways to put these defect edges in. That's because of the type, The defect edges are tightly constrained because of all the information we know about them, because of the careful way that we define the canonical paths. So overall, you get this polynomial factor because m is at most n squared. So this is a polynomial in n times the number of graphs in the original state space, and that's how many encodings you have as an upper bound. This proves the critical lemma, which proves everything else. So you get rapid mixing. Okay, so that's how our definition gives us rapid mixing. And here's two sufficient conditions that we found quite useful. We use this quantity called J of D, which is the sum of the highest delta entries in the degree sequence, where delta is the maximum degree. And then we have these two conditions. If the sum of the degrees is strictly bigger than twice this parameter plus 18 times the max degree plus 56, then we know the degree sequence is 8-8 stable and we get rapid mixing. And if it satisfies an easier condition here, then the degree sequence is p stable and strongly stable. So these are things that are easy to apply for a given degree sequence, whereas, you know, checking, So these are just some other sufficient conditions. And the proof uses the switching method, but I won't say anything about that. Okay, what I want to do is give you an idea why this parameter J of D is so useful. This is something that Jane and Nick Wormold have used in their earlier work. So take your degree sequence, and now I do want it arranged in non-increasing order. So the maximum degree is the first one, and J of D is just the sum of the first delta entries of this sorted degree sequence. When we're proving the critical lemma, we often have to check that we don't choose a vertex that's at degree 2 from some other vertex, at distance 2 from some other vertex. So we're looking at the number of paths of length 2 from a given vertex, because that is some sort of bad case. And this number of paths is at most J of D, because if this vertex V has the maximum degree and its neighbors all have large degree as large as possible, you're going to get J of D. But in the old days, I used to use delta, the maximum degree squared, for this upper bound, which is okay if you're working in a sparse graph or a near regular graph, but it's very bad for heavy-tailed degree sequences. And here's my little cartoon graph again, and I'm just going to illustrate how bad J of D, delta squared can be. Even in this really small example, delta squared is 81, but J of D is only 32. So it's a lot smaller, and you can imagine in a really big sort of power law graph, the difference is enormous. So you get a lot of win basically by kind of taking this sum rather than this massive upper bound for it. Jane and Nick introduced this parameter and have used it in enumeration and sampling before. And here's kind of the point. We were able to use our conditions and apply them to heavy-tailed degree sequences, such as something called a power law density bounded or power law distribution bounded degree sequences. So this proved that the switch chain is rapidly mixing for these sequences, and it was the first known proof of rapid mixing for heavy-tailed degree sequences. So that was a nice thing that came out of our work. And we've shown that these degree sequences are stable families. I'll skip over the definitions of these particular parameters and the proof, but I'll just mention, after all this, and I do apologise if I'm going over time, P stability is not in fact the boundary between mixing and rapid mixing and non-rapid mixing. We've known this since the work of Jerome Sinclair and McKay. So there are degree sequences where the switch chain is rapidly mixing, but the thing is not P stable because you can blow up the size of the state space by making a small change. And more recently, Peter Erdős and co-authors gave more general families for which the switch chain is rapidly mixing, but the families are not P stable. So we know that even though I find this question interesting, the connection between stability, it might not necessarily be, well, we know it's not the boundary between where the switch chain really rapidly mixes or not. And here are some questions. Does the switch chain just mix rapidly everywhere? I kind of think probably not, but we don't really know the answer. Can we find any algorithm, not necessarily Markov chain, which is efficient for any degree sequence? All of the algorithms we know about have conditions. And can this very new approach of Tikhomarov and Youssef be extended to non-bipartite or irregular graphs? That's it. Thank you very much.
Thank you so much, Catherine. Let's go ahead and thank our speaker. And while we're thanking our speaker, I'm just going to go ahead and turn off the recording.